All right, so I know there's at least one person here. If there's anybody else who's in here live, if you guys have any specific questions, we can start with those. Otherwise, I'll probably just start with some of the hypothesis testing ones on practice exam B. So wait for a second here and see if I got any questions that come in. All right, don't think so. So let's go down here and let's start with number 9. Okay. The whole exam was the question. Okay. We'll do some hypothesis testing, and hopefully this helps a little bit going over some more questions. So the first question on 9 is we have this population proportion of dog owners, and we're trying to figure out, we take a sample of 100 households, and we want to know where this population proportion is, but all we have is the sample proportion from the 100 households that we have. So we found that sample proportion to be 0.5. Number 9, we want a 95% confidence interval. Okay? So, the first thing we want to think about, I could do, or a question that could be asked, is let's say that instead I didn't tell you that the sample proportion was 0.4, but I told you that 40 out of 100 households own dogs. You should be able to determine that that sample proportion is 40 out of 100. Right? Or that sample proportion of 0.4. Okay? So what we want to do with a confidence interval is take that sample proportion of 0.4 and build a range around it, come up with a lower and upper bound, where we could say with 95% certainty that the true population proportion is somewhere in this range. Right? Well, how do we find that lower and upper bound? Well, let's go to the equation sheet. So, actually, let me zoom in on this while I'm on here for a second. Thought I had everything zoomed in, and I must have forgot to do this one. So, let's look at that formula sheet. We've got 3 equations for confidence intervals. So, which one should we use? Well, we're dealing with a sample proportion, so use the confidence interval for a sample proportion. I know my sample proportion I found was 0.4, so I plug that in here. The sample size was 100 n, so I plug that in. The only thing left I have to find is this z-score. So I believe if we go back to the problem, it wanted the 95% level, confidence level. So how do we get alpha? Alpha is the area outside of the interval, or the probability of being outside the interval. So a 95% confidence interval, 5% is outside. In terms of a probability or decimal form, that's 0.05. So our alpha at the 95% level, you didn't tab that. Oh yeah. So at the 95% level, alpha would be 0.05. Okay. So alpha here is 0.05. If we divide by 2, that's 0.025. So we're dealing with a sample proportion. It reminds us we need to use that standard normal or z table. So we go there. I know the area that I want in each tail, which is 0.025. You can come in.
Are you recording?
Yeah, but the camera's on.
Oh, I don't interrupt you.
It's okay. So we know the area that we want in the tail, which is 0.025. So we have to look at that area up here. So we try to find what's closest to 0.025. Looks like it's right here. So go over what z-score would give us that. Negative 1.96. So that z-score we want, that gives us alpha over 2 in the tail, is negative 1.96. Now if we go to the formula sheet, anytime I look up that alpha over 2, I'm always going to find that negative z-score. But if we look at this, it's already built in, right? My lower bound is when I subtract this margin of error. My upper bound is when I add this margin of error. And so it's negative 1.96, but I really just plug in the 1.96 there, right? So if I've got that 1.96, what I'm doing is I'm taking the sample proportion, so we can get this to focus a little bit better, add and subtracting that z-score for alpha over 2, times the sample proportion times 1 minus the sample proportion over sample size. Get to focus there a little bit. Where this was kind of our margin of error. So I plug in my 1.96, my 0.4, 0.4, 0.4, sample size is 100. Once I have everything plugged in, it's just a matter of getting that entered into my calculator. And this webcam is not cooperating. There we go, maybe. All right. So that's really just identifying the correct confidence interval and then plugging things in. The only hard part was finding that z-score. So yeah, so alpha is not 0.5, alpha is 0.05. Right? So I had a question kind of asked, remember, alpha is the area outside the confidence interval, but in decimal form. So if I want to do a 95% confidence interval, there's 5% outside the interval, and in decimal form, 5% is 0.05. Right? So then I divide 0.05 by 2, I got 0.025, and then that was the value I looked up in the table. Does that answer your question? I don't know what your name is. I don't know if I should refer to you as Gator Melon. I'm not sure that's how academically professional that is. Yep. Alpha is just the percent. So Julian, so the alpha is just the percent outside the confidence interval. But when we're dealing with alpha, it has to be in decimal form, which is why 5% we use the alpha of 0.05. Right. So if we plug those in, we kind of have the answers worked out here, which is nice. But once we plug everything in there, we should get about 0.304 and 0.496. Okay? And that's where that 1.96 came from. Okay? So on 10, we've got a question where we have to identify the null and alternative hypothesis. So the national media reports 36% of families own a dog. You want to test whether or not that population proportion is greater than 36%. Right? So what you want to test for is whether or not that true population proportion is greater than 36% or 0.36 as a proportion. So that's your alternative hypothesis. That's what you want to test for. So you go down here, your alternative hypothesis is that proportion greater than 0.36. You assume the opposite is true for the null hypothesis, so less than or equal to 0.36. And this will be our null and alternative hypothesis here. Okay. Now, we're still using the information we found up here. Right, use this in the next 5 questions. So the sample proportion we found was 0.4 out of 100. And we want to test for whether or not this is true, or test against whether or not the null is true. So the type of test always comes from the alternative hypothesis. So we look at the alternative hypothesis. We have a greater than sign. So greater than sign means right-tailed test. Okay. So once we get to 11, right, we're looking for critical values. Where's my eraser? Here it is. So when we're looking at a right-tailed test, automatically we should know our critical values need to be positive, because we want critical values that give us alpha in the tail. Right? So we can look up the very first one, because I think what I asked was what are the critical values at the 10, 5, and 1% level? So let's just do the first one, 10%. Alpha would be 0.1, so it's very similar to confidence intervals in the sense that alpha is in decimal form. So what would give us 0.1 in this tail? Well, we know we're looking at the right side of the distribution. Remember, the mean of z-scores is 0. And critical values are just z-scores. They can be t-scores if we're dealing with a student t-distribution, but either way, they're coming from this distribution of z or t-scores. So if we have a right-tailed test, critical values are positive. If we have a left-tailed test, they would be negative. Right? So which of these are potential answers? Well, right away, right-tailed test, it's either B or C. Right? And this is where on the Canvas exam, I'll kind of ask you to identify a null or alternative hypothesis, but then like in 11, I would give you an assumed true, null, or alternative, because if you got 10 wrong, like let's say you answered A, well now it's a left-tailed test, you would get the critical values wrong. So I'll kind of give these assumed true values in the Canvas one to prevent cascading errors, basically. So we've got 10, 5, and 1%. We just looked up we can look up the alpha of 0.1. So we go to the table, and honestly, we might start, oh, here we go. We might start remembering these, all right? So we want the area in the tail to be 0.1. Now there's two ways we can do this. One, well, we actually want 0.1 in the upper right tail, which means that we want 0.9 in the left tail. Right? We wanted 0.1 in the upper right tail for our right tail test. So we could look up 0.9, see where we get closest to that. Looks like between these two values. So 1.28 and 1.29, take the higher of the two, 1.29. Or we could say, okay, well, I can just look up 0.1 and remember that, oh, I don't want 0.1 in the lower left tail, I want it in the right, so whatever z value I find, looking up that area of 0.1, if I want it in the right tail, it's that same value but positive. So sure enough, if I look up where's 0.1, how can I get closest to that? In between these two, so negative 1.28 and negative 1.29, it's a right tail test, so use the positive 1.29, so got the same value. The third way I can do it, not to add too many complications, but I think it's a little bit easier to do it this way, at least for me, and these are the numbers I display. If I go to this last row of the student T table, I can actually get it out to the 3 decimals. The areas I wanted in the tail was 0.1, 0.02, sorry, 0.1, 0.05, and 0.01, so these 3 columns. So I go down to the very last row. These represent the standard normal or z values I would have found, so 1.282, 1.645, and 2.326, which is ultimately how we get this answer to B. Okay? Pause here and see if I get any kind of lagged questions. Any questions on that? Now, one thing that I could do differently here. Okay, I got someone starting the question. Maybe. Okay. So those are our critical values, right? And that they're positive. So we've got 1.282, 1.645, and 2.326. So when you do the percentage, you're estimating instead of using numbers in the left column and top. So when do you... Oh, I gotcha. So how do we know, the question was, how do we know when to kind of use these numbers on top or use the numbers in the middle, and kind of the tables are a little bit different, right? So this is I'll try to explain it, maybe even writing this down might help, right? So in terms of hypothesis testing, when we want to find the p-value, which we haven't done yet, but if we want to find the p-value, we will have a test statistic. That test statistic will be a z-value. So if we have a test statistic and want to find a p-value, that's where we use the kind of labels on the rows and columns. Then we look up that test statistic. Let's say it was negative 3.1. We'll look up that test statistic and say the p-value, the area to the left of it, is 0.003. If we want to find a critical value is a z-value. So now we're working backwards. Now we know the area in the tail, so we know the area in the tail, or we know one of these numbers, right? The number we just looked at was 0.1 for alpha. And then once we looked up the probability or the area in the tail we want, then we go over and up to get our critical value. So when you're finding a critical value, you use the numbers in the middle here. If you're finding a p-value, then you look up using the row and column headings. For the t-tables, it's kind of backwards, which is kind of, a little confusing. But now if we wanted to look up a p-value, well, here these represent t-values, just like here these represented the z-values. So now if we want to find a p-value using the student t-distribution table. We'll look up our test statistic here, then go up to the column to see what that p-value is. If we want to find a critical value using the student t-distribution, well, now we know the area in the tail, which is what these column headings represent. So if we know the area in the tail and want to find a cutoff value, that's a critical value. So look up the area we want in the tail here, then go down and find the critical value. Does that help clarify a little bit, at least kind of between the two different tables? I know there's a 4 or 5 second delay. Okay, good. All right, that was a good question though. And kind of walking through each table is probably a good thing to do there. Okay, so we've got our critical values. And the next thing we do is find our test statistic. Now, honestly, I think the test statistics, calculating them, should be some of the easier points in this exam, because really it's only identifying what equation you need to use. And if you see this word test statistic, and you go to that formula sheet, maybe even right here, write it up, print it. You can print it out on your own. This time, I can't hand them out, so if you can, print these out somewhere. I don't know if you have a printer at home, or if you want to like download the file and then start kind of typing things in a Word document, that's okay. But these, in the bottom right corner, these are your test statistic equations. We're dealing with a sample proportion. Remember, this whole thing was like started out the proportion of dog owners. So the only test statistic equation that has proportions in it is this guy down here. Okay. So someone asked if the test will be in Respondus. I'm going to try not to use that, only because I already can envision you guys are going to need these materials, and if someone forgets to download them ahead of time or doesn't have something that can open the PDF and relies on the web browser, that's going to be an issue. But because of that, I might, I'm going to make sure that I have some questions, or the way I write the questions aren't going to be like easy to Google. You can imagine every question I write, I will do a quick Google search on my own to make sure that it's not easy to solve. But yeah, I won't be putting it on, so I still need to play around with it a little bit. If I can put it on Respondus and have these, still have you able to access, I think it should just shut down your web browser. But if I have these up in a form that you can download, or at least you can view, then I might use Respondus, but I'm going to double check, because I don't want anyone getting locked out of these of this formula sheet or of the tables. Yeah. But I'll make that known in the announcement when I later today, when I have the kind of test all ready to go, and I've played around with some of the settings a little bit. So every active program, okay, yeah. Like I said, I'm going to try to see if I can play around with the settings and if I can get it so that it allows certain programs and not others, because I think there's a way. I'm pretty sure there's a way to do that. I haven't ever had to use it in the past. But I think you can, because I think I talked to someone who allowed Excel in it. So we'll see. I'll kind of play around with some of the settings for looking away from the screen to look at the physical sheets. Okay. Well, I may not end up using Respondus then, so I wouldn't worry kind of too much about. I don't know. I'll trust you guys somewhat, right? So. Even if you have Google at your fingertips, I'll write it in such a way that kind of makes that known. So, but yeah, I likely won't be using Respondus because of some of these issues that you guys are mentioning. So don't. I hadn't planned on using it. Okay? So like I said though, what I would do though, I know you can use this in the web browser, but it might be better to like download them and then like maybe write on them, or print them out and write on them. Either way would probably be beneficial. Right? So this way you guys get a little bit of an added bonus that you usually wouldn't get, which is you can have a formula sheet where you've kind of written some things down on it. Right? All right, so here's our test statistic equations. We are dealing with that sample proportion, so we're going to use this guy right here. So once we know that that's the equation we're using for this test statistic, all we need is this hypothesized true value of 0.36, our sample proportion of 0.4, and our sample size of 100. Once we have that, it's really just a matter of plugging it into that equation, right? So this was our equation that we're using. The p subscript 0, that's the assumed true proportion, so that was 0.36. Sample proportion was 0.4. Sample size was 100, right? So this, we got everything we needed plugged in. So we plug everything in, we get about 0.83. Right? So 0.83 is our test statistic. Okay. What's the next question? So what would the p-value be for this hypothesis test? Okay, so the question that was asked earlier is kind of nice because it leads us into how would we solve 13. Well, if I'm looking for a p-value, and as a reminder, we're dealing with proportions. Anytime we have an example of proportions, we're using that standard normal or that z distribution. Okay? So we go to the z table or standard normal table. The test statistic we found was 0.83. Now, on the exam, once again, to prevent cascading errors, I might give you an assumed true test statistic at this point, right? So then you could look up that assumed true test statistic. So 0.83. So we go down here, 0.8, then go over 0.83, and the area to the left of 0.83 is 0.7967. All right, but we're dealing with a right-tailed test, so we don't want the area to the left. We want, sorry, the area to the left. We want the area to the right for a right-tailed test. So 0.7967 is the area to the left of our test statistic. So I'll redraw this. Everything we've got going on here. So, first thing, we found 0.83. We had a right-tailed test. So when we looked this up, we found 0.7967, if I'm remembering this number correctly. We wanted the area to the right for a right-tailed test. That represented our p-value. So 1 minus 0.7967 or 0.2033. Right? So that's our p-value. Okay. So remember, we only reject if the p-value is less than alpha. So I know the problem didn't ask for this, but I said there will be a short answer kind of component of this exam, and so you're going to have to work through a hypothesis test kind of on your own and eventually get to a rejection decision. So this is, I only reject if the p-value is less than alpha. So with a p-value of 0.2033, the usual alphas I look at are 10% or an alpha of 0.1, 5%, which is an alpha of 0.05, and 1%, which is an alpha of 0.01. If I look at 0.2033, it's less than all three of those, right? So I can reject the 99, 95, and 90% confidence levels, or I can reject at the 1, 5, and 10% significance levels, right? It's two different ways of saying the same thing, okay? So I can, I said I can reject. I fail to reject, at all levels because this clearly is not less than these. I only reject if my p-value is less than these three values. Here at 0.2033, it's not less than any of these. Right? Sorry, I think I misspoke earlier. I was just kind of thinking about if this was true, that's what we would do. But in fact, the actual p-value we had here was much larger than all three of these. Okay? So our p-value is not less than our alphas here, so we fail to reject. The only way we reject is if this is true. Yeah, sorry for kind of saying that backwards. I was thinking of the scenario if we had something that was less than all three, but in this case we had a p-value that was not less than all three. Okay. So, not less than these, we would fail to reject at every single level. Okay? But we found our p-value, which I think was the only thing that the question actually asked for, right, of 0.2033. So this is the only condition for rejection if we're using the p-value approach. If this is true, if the p-value is less than alpha, we can reject at that level, right? We can compare it to several alphas. Now the other way we could do this, let me grab another colored marker. I think this might help with a different color. So we also had critical values that we had found, which were like 1.28, 1.65, and 2.5 something, I think. So here's our rejection regions, anything to the right of these three critical values. This was a alpha correspond to an alpha of 0.1, 0.05, and 0.01, right? Those are our three critical values. We talked about that in the problem earlier. So the other way we can determine rejection is the critical value approach, which is plot your critical values. The area that's more extreme than your critical values is your rejection region. Now here, the rejection regions are to the right because it's a right-tailed test. If this was a left-tailed test, it would be the area to the left of our critical values. So after you plot those critical values, determine where those rejection regions are. If your test statistic falls in that rejection region, you can reject. Here, we quite clearly have a test statistic that's way outside those rejection regions, so we would fail to reject at every single level, which is what the p-value approach also said we should do. Those approaches should always give us the same answer, right? And if you go back to the recorded lecture, the end of the first recorded lecture from last week, and the beginning, I think, of the second recorded lecture from last week, I had kind of a nice drawing where I kind of had it so you could see why the p-value and critical value approaches always led to the same decision. Because really, if I compare the p-value, well, when I had this critical value, this corresponded to a certain alpha, right? So if I compare alpha to the p-value, I can get a rejection decision. So I could, kind of compare areas here, or I could compare what's on the x-axis. I can compare the critical values to my test statistic. So either compare these, or I can compare kind of these. And either way, it's, those two things are tied to each other. So I'll end up with the same decision. Any questions on that one for those of you who are kind of signed on here? Okay. So let's instead say we had an example where it just needs practice a few more times. Okay. So you've got IQ, it's normally distributed. You have a population standard deviation of 15. Okay. You take a sample of 49 students, and you find a sample mean IQ of 109. So you somehow have this known population standard deviation. You've got a sample mean, right? Should I use the standard normal or student t? Well, if we go to the formula sheet actually kind of reminds us of this. So if I look at like either my confidence interval or my test statistic equation, so confidence intervals, test statistics, notice when I have a sample mean, I have two scenarios. I either know the population variance or I only have the sample variance. We were told, or you could also say if I have the variance, I also know the standard deviation. So we were given a population standard deviation. So if we wanted the population variance, all we would have to do is square that. So because we have that information, it kind of reminds us, oh yeah, you're using that z, or it reminds us here, you're using that z, or standard normal distribution, right, or z tables. So here we should be using that standard normal distribution because the population variance is known, right? If we know the standard deviation, we automatically also know the variance because we would just have to square it, right? So B is going to be our kind of correct answer there. These other ones don't really apply because we only use that student t distribution if we have a sample mean and we don't know the population standard deviation and we only have a sample standard deviation or a sample variance. Okay? So we're going to use the standard normal distribution, which makes life a little bit easier. So if we want to do a 90% confidence interval, right, it's going to be very similar to what we did with a proportion. It's just a slightly different equation. Right? So I go to my formula sheet. I'm trying to find a confidence interval, CI, confidence intervals. I've got a sample mean, and I know that population standard deviation. Right? So I can plug my sample mean in, plug my population variance, plug in my sample size. Or we didn't have the variance here, so I actually would just plug in my population standard deviation. So I'd still need to square that when I'm doing the math out. The only thing left I have to do is find the z value. Right? So what confidence level do we want? 90%. So if I wanted a 90% confidence interval. And the equation kind of reminds me of this, but what would my alpha be? So if I have a 90% confidence interval, and I'm building this around, what, I think it was 109 was the sample mean that we found. So what I want is within this range, there to be 90%. So outside this range, there should be 10%. In decimal form would be an alpha of 0.1. But right, I have two tails, so this gets divided into like two sides. So this is alpha over 2 on each side, or 0.05. Right? Oh, there we go. So the area that I want in these tails is 0.05. Right? So what z-score would give that to me? Well, sorry, I'm getting this whiteboard down here. Try not to hit the bell. So I've got the area that I want, 0.05 in that lower in each tail. So I know the value. So for confidence intervals, it's very similar to looking for critical values, right? Because in both scenarios, we're looking for a z value. So I'm looking here for 0.05. Looks like it's in between these two values, right? So negative 1.64 and negative 1.65. We'll take the higher of the two and we'll do 1.65. Now, remember, it is negative 1.65, but these positive and negative signs kind of already built in, right? The negative 1.65 would give us the lower bound. The positive 1.65 would give us the upper bound, right? So once we have that z value, right, we actually have everything we need. It's just a matter of plugging everything in and getting our lower and upper bound here. Okay? Any questions on that one before we keep moving? I kind of blew it up here so we can see it a little better. Okay with that? All right. So the next question is, after we have this confidence interval, right, let's do a hypothesis test instead. So we want to test for whether or not the average IQ is different than the national average of 105. Right? So our Ball State students kind of different than the average. So we have, is it different than 105? Anytime we see this word different than with hypothesis testing, should automatically be thinking about, is it not equal to, right? Is it different than this number? So is it different than 105? Is it not equal to 105? So our alternative hypothesis, and here I wrote it as H1. On the exam, I'll always write it HA to be clear that it's the alternative hypothesis. You'll see it written this way, though, elsewhere. So I kind of mixed it into this second practice exam. So is it not equal to 105 as our alternative, which means we assume the opposite is true for the null, or that the mean is 105. So now that we have this not equal to sign, we should automatically be thinking, okay, not equal to sign of the alternative hypothesis means we have a two-tailed test. Okay? So two-tailed test, the previous one we had a one-tailed, it was a right tail, but it was one tail. Now we have a two-tailed test. So what should the critical values for that be? Well, for a two-tailed test, we have pairs of critical values at each alpha. Okay? So here at the 10, 5, and 1% levels, our alphas are 0.1, 0.05, 0.01. And those are the area that's in our tails now. Before that, it was just the area in our tail. But now we have two tails. These are going to be that's the area in our tails. Right? So for a two-tailed test, we're going to see, actually, this looks pretty similar to probably what we were doing with the confidence interval. So we've got a known standard deviation. So we're looking at a standard norm or a z-table. The critical value will be what gives us alpha total in these tails, right? And it's going to be the same value on both sides, but one's positive, one's negative. So we have a pair, right? It's the same value, but one's positive, one's negative. And it gives us alpha total in the tails. So on each side, we would have alpha over 2. Right? So let's say for the first one, alpha was 0.1. and each side we'd have 0.05. And actually, it's the same exact thing we just looked up from the confidence interval, right? We can go to the table. So if I go, oh, where is it? Here we go. If I go to that z table, and I wanted 0.05 in the, that's the area I want in the tail. So I go down here. Oh yeah, negative 1.64 and 1.65. So I'll take the higher of the two, negative 1.65. So I've got negative 1.65 approximately, 1.65 over here. That's going to be my first critical value. Now if I wanted the next alpha of 0.05, I can probably identify what the correct answer is just by looking up that first one. But if I wanted to prove it to myself, well, if I want a smaller area in the tail, what has to be true? Well, my critical values are going to be out a little further. So now alpha over 2, there's going to be 0.025 in each tail. Right, so, oops, wrong button, maybe, there we go. So now I look at 0.025 as the area that I want in the tail, so it's right here, negative 1.96 is my second critical value. I could look up the third, but at that point, I can probably already identify, I can already identify that these are the first two. I could look up the third and then find about, negative 2.57 there as well. Okay. So right away I could cross out A and C because I know I had pairs of critical values, but then I actually looked up what those values are. It'd be B and D here. Okay, so we've got our critical values, right? We could plot them just like we did in the previous problem and then put the test statistic up against those, right? So I'll do that first, right? So let's get everything plotted here. I'll kind of write it out, draw a little bit bigger. So we just looked up, this black marker is dying on me. I can't really go to the office they're locked up in the supply closet, so and no one's there. So we just found 1.28 approximately, 1.65, nope, I lied to you. This was 1.65, this was 1.96. There we go. Then over here, negative 1.65, negative 1.96, negative 2.5 something. Rejection regions for a two-tailed test. And this is actually one way that I say it for rejection regions. Don't think about it for a right-tailed test, it's area to the right, left-tailed, it's area to the left. Oh, we got some questions, hold on. So, you're going fast for me. All right, I think someone answered it. So our critical values, yep, good, you answered it for me. So critical values are only in pairs when we have a two-tailed test. Remember in the previous problem, we had only like one side, we only had one critical value at each alpha. That's because we had a one-tailed or a right-tailed test, right? Or if the same thing for a left-tailed test, you'll only have one critical value at each alpha. But for a two-tailed test, we've got two. We've got a kind of pair of critical values. Okay? So now that I've got my rejection regions here, okay, and the way I was kind of explaining before I looked at the chat, I always say it's the rejection region is the area that's more extreme than the critical value, because for a right-tailed test, the area that's more extreme is this way. For a left-tailed test, it's not actually greater than going this way, right? Because we're going to a larger negative value, so it's actually going down. But if you just think about it as the area, or going to the side that's more extreme, so more extreme or larger in absolute value, like a more negative value. And then for two-tailed, kind of being more extreme than your critical value means kind of going in either direction there. So now the only thing left to do to make our rejection decision is where's the test statistic, right? So I'll cover how we calculate this one, but I think if we do, it's negative 1, or wait, it would be positive 1.86, hopefully. If not, that's a good number to give us an example though. So I've got positive 1.86. The next step to make my rejection decision that I do is I plot that. So where would 1.86 be? So here's my test statistic. Okay, so it falls in my rejection region for that critical value, which corresponded to, if we kind of remember, here's my alpha of 0.1, here's my alpha of 0.05, here's my alpha of 0.01. So it's in that rejection region at the alpha of 0.1 or the 10% level, but it's not in the rejection region. If you can't quite see it, my cutoff was right here. So it's not in the rejection region for alphas of 0.05 or 0.01. So we would fail to reject at the 5 and 1% levels and only reject at the 10% level. Right? And kind of the whole overarching idea of this was we started out assuming, you guessed the test statistic, but where did you? Oh, yeah, sorry. I jumped ahead here real quick just so I could kind of do all the drawing there. The next question would have been, what's our test statistic? So how would we have calculated our test statistic? Well, we go to the formula sheet. Here's our 3 test statistic equations. Remember, this was the scenario where we had a sample mean and we were only given a population standard deviation. So we knew the population standard deviation, so this was the one that we used. Okay? So plug in our sample size. I think it was, I can't remember exactly. We'll see in a second. The assumed true mean was 105. The sample mean we found was 109. The sample standard deviation, so just that sigma guy there, was 15. And then the sample size was 49. Okay. So if we plug all those in, hopefully I guessed it right. I kind of, yeah. So plug those values in, 1.86. So that's where that came from. Okay. Yeah, sorry, I jumped ahead there so I could, since I already had the graph up there. So this is a good scenario where if you had gotten that test statistic wrong, and I asked you to make a rejection decision, you're not going to get that right. So I then say, okay, assume that you found the test statistic was negative 2.3. Now notice, when I give you these assumed true values, they might not be related at all to the previous, what the actual test statistic is, right? 1.8, I gave you a negative value here, right? So don't read into any of the assumed values that I give you. I'm probably choosing them for very different reasons that have nothing to do with what the actual test statistic value was. So assume you found it was negative 2.3. Okay, well now what would your rejection decision be? Well, now if your test statistic isn't 1.86, instead it's negative 2.3, well now here was negative 2.5, negative 1.96. So if I plot it, now my test statistic is somewhere over here. So now it's in the rejection region, and once again, these were alphas of 0.1, 0.05, and 0.01. Okay. So now, there we go. So it's in my rejection region at the alpha of 0.1 or the 10% significance level, so I can reject at that level. It's in my rejection region for an alpha of 0.05, so I can reject at the 5% level. It's not in my rejection region for the alpha of 0.1, so I fail to reject at the 1% significance level. Right? So critical values, I think it's a nice, easy visual, but we could have also made the rejection decision here, so reject, reject, kind of fail to reject. We could have also made the rejection decision using p-value. So what was the p-value? Like, what did it represent visually? It was actually the area that's more extreme than your test statistic. Once again, I say more extreme. You could think about larger in absolute value. So it would be, here's my test statistic. The p-value would be the area to the left of it. But for a two-tailed test, it's not just this area, because seeing a test statistic or something this far away from the assumed true mean, it was equally as likely we saw something that was this far away from the assumed true mean, right? 2.3 standard deviations away from the assumed true mean, but in the other direction. So when we find this area for a two-tailed test, this only represents kind of half of our p-value. We would have an area over here as well. That would be to the right of positive 2.3. So once we find this, we multiply it by 2. Right? So hopefully that leads us to the same rejection decisions. So if we go to standard normal distribution here, now I'm looking up the p-value. So now I know what my test statistic is. It was negative 2.3. So negative 2.3, and the second decimal there would be 0. So negative 2.30, 0.0107. So that was the area in this lower left tail, right? So this area over here in the lower left tail, 0.0107. I said that's only half of it. We have to multiply it by 2. So 0.0107 times 2 is 0.0214. So this is our p-value. We only reject if the p-value is less than alpha. So which alpha values is this less than? Well, is it less than 0.1? Yep, so we would reject at the 10% level. Is it less than 0.05? Sure enough. So we reject at the 5% level. Is it less than 0.01? No, so we would fail to reject. Right? So it leads us to the same rejection decisions. Okay? Any questions over that before we kind of keep going? So we've seen a couple different types of examples here. Was there only 19 questions on this one? Double checking. Yeah, there was. So what's something else I could kind of go over real quick? Let me pull this up. So I've got one more type of example that we could do. So let's say we saw I'm going to walk through the previous one, but let's say now instead we don't know the population standard deviation. So if we go back to, there we go. We go back here. All I'm going to do, I got to learn how to use hotkeys better and not put them in my Word document. So let's see. So instead of having this known population standard deviation here, let's say we only had a sample standard deviation. So what's going to change? Well, I can kind of walk us through. The steps are all going to be the same. I just want to point out a couple little things that would be different. The steps, everything is going to be pretty much the exact same. So now, do I use a standard normal or student t? Well, now I only have a sample standard deviation. So instead of using the standard normal, I actually am using the student t because I don't have a known population variance, right? This is because I changed the example, right? This is like me basically giving a whole other set of questions here you could think of. So now I only have a sample standard deviation, so now the answer would be D, right? So basically kind of giving you a part of a third practice exam here on hypothesis testing. How would I do the confidence interval? Nothing changes here. It's the exact same thing, except when I go to my confidence interval equation, well, now I only have a sample variance, and it tells me you don't need to look up a z value, you need to find a t value. Right? So now I still look up the area of alpha over 2. So for the 90% confidence interval, we said the alpha was 0.1. So divide that by 2, 0.05. So I want the area of 0.05 in each tail. But now we have one more thing we have to worry about, which is our degrees of freedom. Okay? So why did I choose that student t question? So I chose the student t because when I went back here, I changed the original problem from having a known population standard deviation to only having a sample standard deviation. And the reason why we had to use the student t, if we go kind of way back to the whole reason why we had to use it, remember, when we're creating when we're creating like, let me see, I'll show you this. When we're creating like test statistics, we're trying to get a mean of 0 and a variance of 1, but because we have a sample variance here, we're actually when we calculate the sample variance, remember it was divided by n minus 1 instead of n. So even if we had perfectly captured what the true population variance was with our sample variance would still be an incorrect measure, right? Because it should have been only divided by n, and we were dividing by n minus 1. And so even if we perfectly captured with our sample what the population variance was, when we calculate the sample variance, it would be a little bit off, right? Going way back to the first exam, remember we said dividing by n minus 1, it makes it a little bit higher, right? Because you're dividing by a slightly smaller number, which means that this denominator, dividing by the standard deviation, doesn't get you a mean 0 variance of 1. It gets you a mean 0, but a variance that's a little bit higher than 1. And how much higher than 1 depends on what the size of the sample was. And this is because, dividing by 99 instead of 100 isn't as big of a deal as if you divide by 4 instead of 5, that has a much larger impact. And so that's why we use the student t there. So hopefully that kind of clarified. So now that we've got the area that we want, which is 0.05, we need our degrees of freedom. So degrees of freedom is just n minus 1. So if we had a sample size of 49, right, our degrees of freedom will be 49 minus 1. So 48. So we go here, and we say, okay, the area we wanted in the tail, right, if we look at this, the area that we want in the tail now, or each tail, was 0.05, but our degrees of freedom was 48. So now, the t-value that we should be using right here would be that 1.677. Okay? So once I identified what alpha over 2 was, or alpha divided by 2, which is 0.05, my degrees of freedom was the sample size minus 1, so 49 minus 1 is 48. The t-value that would give me those desired areas in my tail, 1.677. Right? So that's the only thing that would change, really, is instead of using that z-value, I could use a value from the student t distribution. So that changed a little bit of what we had to do in 15. 16 doesn't change at all. I still identified the null and alternative hypothesis the exact same way that we talked about before, so we're still dealing with this two-tailed test with assumed true value of 105. How do I find critical values? Well, this changes a little bit, right? Because we found the critical values before, by looking up these areas, right? And because it was a two-tailed test, there was half of alpha on each side. We looked up alpha over 2 essentially to find these. And they got a question. Yep, degrees of freedom is just the sample population, but sample size minus 1. So if we look at the formula sheet, it even kind of reminds us of that right here in that confidence interval equation, sample size minus 1. Yep. So now instead of looking up the values on the z table, the only thing that would change now is we look up these 3 alphas divided by 2 because it's a two-tailed test, but on the student t. So we've got degrees of freedom of 48 still. That hasn't changed. And now if we divide each one of those alphas by 2, we had 0.05, 0.025, and 0.005 were the 3 areas that we wanted. Okay? So I go down here, 1.677, 2.011, and 2.68. Right? So we look them up the same way we did before. Right? We had alpha over 2 because of a two-tailed test. It's just now we have a degrees of freedom of 48. And before I told you we could have used degrees of freedom of infinity when we were using that standard normal or the z table or the z distribution. Okay? So the same process though, once we have those 3 values, it's a two-tailed test, so it's those values but pairs of those. So it would then be, kind of notice, it would actually be these values right here. So if instead we had the sample variance, these would have been our critical values. We plot those just like we did before. We want to plot our test statistic against it. Well, we're still actually, for the test statistic, notice what's going to happen. Well, if I didn't change the values and I just, instead of having the sample, instead of having the population standard deviation, I had the sample standard deviation, notice these equations are exactly the same once I plug the numbers in. It's just that this now represents something coming from a student t distribution, while this one represented something coming from the standard normal. So once I plug those values in, I'll actually get the exact same test statistic. So that would still be 1.86. I would now plot that 1.86 against these critical values, but ultimately it's going to end up leading to the same rejection decisions, right? They are a little bit different, right? But not different enough to change our rejection decisions with those different test statistics. Now, the one question that's not on here that could be difficult that I kind of added into the discussion was, what if we wanted to find the p-value? Well, let's say I had this assumed true test statistic of negative 2.3. How would I find the p-value using that student t distribution? Well, my degrees of freedom is still 48. Okay, let's see if I can get this on the same screen. There we go. But now I have my test statistic and I want to find the area in the tail. So now I'm kind of like working in reverse. So if I try to find negative 2.3, well, first of all, this always is just giving us the area in the right tail. But it's a symmetric distribution, so these values, I could make an exact same student t-table, but all negative, and it would still be the same, right? It's symmetric. So degrees of freedom 48, but I can't even find 2.3. It's in between these two. So what that is telling me is the p-value has to be somewhere between 0.025 and 0.01. I could actually put a bounds on my p-value. I said I'm not going to make you do that on the exam. So if I asked you for a p-value when you're using the student t-distribution, I would have to do something like this. Assume that the test statistic is 2.011. So, or let's say I do negative, right? So let's say I change this. Assume that the test statistic is negative 2.011. What would the p-value in rejection decisions be? Maybe that's the question I ask. So at 2.011, okay, remember it's symmetric, so the area to the right of positive 2.011 is the area to the left of negative 2.011. That area is 0.025. But remember, the same principles still apply. It's a different distribution. The numbers will be different. But for a two-tailed test, I just found the area here was 0.025. I have two tails, right? So I can find this area, but I then need to multiply it by 2. Right? So I found that for that assumed true test statistic of negative 2.011, the area to the left of that would be 0.025. That's only one of my tails, so I multiply it by 2, and 0.05, there would be my p-value. Okay. Now, I'll also kind of point this out, because I'm glad I chose that one because it brings up this additional issue. If I have 0.025, and then I multiply it by 2 to get my total p-value, what levels could I reject at? Well, we only reject if the p-value is less than alpha. So 0.025 multiplied by 2, my p-value is 0.05. So is that less than an alpha of 0.1? Yep, so I can reject at the 10% level. Is it less than 0.05? It's actually not less than 0.05, right? It's equal to, so I actually would fail to reject there. This doesn't look a whole lot different than my R. I would actually fail to reject there at the 5% level. And if I'm failing at the 5, I'm for sure going to fail at the 1 because is 0.05 less than 0.01? No. So I would fail to reject at the 5 and 10% level and only reject at the 10% level here. So things changed a little bit, but it's overall the same kind of process there that we were using even when we had a known standard deviation, known population standard deviation. Like this drawing will look the same, it's just now the numbers will change, right? We'll have different critical values because we should be using that student t-distribution. All right. Here, maybe we can get you to say, come here. Can you say hi? No? You're going to hide? Can you say hi? Hey, come here. Okay, you're being shy. All right. I was trying to get the dog to say hi, but I guess not. Okay. All right. So that kind of does it for this practice exam, these practice problems. I just want to take the time to go through the critical or the hypothesis testing once today because I think that's probably the most difficult kind of subject matter for this upcoming exam. I would, like I said, I would expect as you're going into this, the first half of these practice exams will look very similar to the first half of the of this exam. The rest of it will look similar, but I will have a short answer question where I ask you to do one of these 3 types of hypothesis tests in terms of either a proportion, a sample mean where I know the population standard deviation, or a sample mean where I don't know it, right? So I'll ask you to do one of those as the short answer, and you'll have to work out everything, right? And you can choose either the critical value or p-value approach, but you have to ultimately work to a rejection decision, which means identifying the null and alternative hypothesis correctly, calculating the test statistic, and then you either use the test statistic and the critical value, or you use the test statistic to find a p-value, and then make your rejection decision. So is there anything in the test that we didn't cover today? So there is. right? Today, we didn't cover the first half of this practice exam. So the last taped exam review I did, we did go over practice exam A, these first like 8-9 questions. So it starts with a uniform distribution, like these ones, and I think if you go back to that recorded lecture, this wasn't too bad, right? If you then kind of look at, okay, what if I take a sample from a actually the next ones were, what if I just look at a normal distribution, how can I determine probabilities being greater than or less than or between certain values? And then if I take a sample from that distribution, can I determine, what's the probability I'm greater than or what's the probability I'm between two values, right? So I would look at the answer key here for practice exam B, but also go back to that first recorded exam review, because I do go over those first 8 or 9 questions from practice exam A that you would see on the exam as well. Okay. Are there any other questions kind of relating to the exam? So my tentative plan is finish kind of writing it up today, like you guys kind of asked. I don't think I'm going to use Respondus, but there should be probably around, kind of like the last one, probably around 25 questions. If you, depending on how you count the short answer, how many questions you would count that as, it's probably like a 4 kind of questions. When is the test open? Okay, so I should be getting it posted. I'd like for it to be up before noon tomorrow. I might even have it released at like midnight tonight if I can kind of get enough done on it today. I just want to, I don't write these on Canvas very often. I want to make sure there's kind of no errors with it, so I want to make sure I take it and work through it on my own as well before I actually release it to you guys. So it should be the very latest put up there by like 10 or 11 tomorrow morning. Once it's up there, you can take it anytime you want, and it's going to be 90-minute kind of time length on it, and you can take it at any point from when it's posted until the end of the day Thursday. So if Wednesday works best for you to take it, choose a time block during Wednesday. If tomorrow works best for you anytime after like 10 or 11, you can take it tomorrow. If Thursday works best for you, you can take it anytime during Thursday. You only get to take it one time. And once you start it, you have to kind of finish it within that 90 minutes. But yeah, so it's kind of allows for some schedule flexibility. Also, well, yeah, it allows for some of that schedule flexibility. So if you just want to take it one day. Yep, Thursday up until midnight. I would say try not to take it too close to midnight. I think with having the deadline set at midnight, I'll allow you to start at midnight. So it might look like you can open it up until 1:30, but that's because I believe the way that Canvas works, when I set that due date, it stops after that. I don't want it to like kick you out of your quiz. So so you can start it at the very latest 11:59 on Thursday. So it'll look like it's open another hour and a half, but that's only because in case someone starts it right at that due date, I don't want it to like kick them out. Okay. You guys said we're super busy. Oh, I don't know. I would absolutely hate taking like 5 classes online. It sounds like a nightmare. All right. Well, I'm gonna stop the recording here. If I have any other questions.